So this is E6980. This is our last lecture, lecture 27. So I'll start by discussing the PLL circuit that you saw in the quiz today. You had a reference connected to the PFD. Instead of the regular capacitor you are used to, you had a resistor R as your loop filter. VCO. This is your out signal. You had a divider in the feedback path, and this was your feedback signal. First part of the question is to sketch the small signal phase domain model. So this is your phase error. This is ICP by 2 pi into R, followed with KVCO by S. This gives you phi out of S. And you have 1 by M in this path. And this completes the phase domain model. Now your L of S expression is ICP by 2 pi R KVCO, M comes in the denominator, into 1 by S. So if you sketch the 20 log of magnitude of this, it will just be with minus 20 dB per decade. And if I look at the angle of L of j omega, that is simply minus 90. So this is basically a first order system, unconditionally stable, provided the continuous time domain is, continuous time assumption is valid, right? Okay, what is the next part? You have to determine the type and order of this PLL. So how many poles are there? Only one pole, right? And that pole is at origin. Therefore, type, which is the number of poles at S equal to 0, is simply 1. So this is a type 1 PLL, and there is only one pole in the system. Therefore, this is a first order PLL. So this is a type 1 first order PLL.
When we calculate S, we know when I calculate L of S, I mean G of S by 1 plus H G of S.
So if the you look at you are looking at whether the closed loop transfer function has poles at the origin or not, right? No, typically you look at the number of poles part of the L of S. And I'll tell you why that is the case, right? So the second part, 1E is where you have to plot the average control node voltage versus phase error. This was actually very straightforward, right? So from, yeah, plot the average control node voltage versus phase error. Okay, so this is, question is from phase error to VC, what is the expression? So that is simply your VC. If I were to write VC of S, this is simply equal to phase error into ICP by 2 pi into R, right? But this is in timing diagram was not needed. You could have directly said this. The only thing is, if you write it as VC of S, then it is in Laplace domain, right? I asked for what is the steady state value. So basically you have to put S equal to 0 in this equation. You are assuming that your phase error is a constant steady state, right? Which means
we don't require all this.
in timing analysis, you would simply, you are analyzing it for a given phase error,
Yes.
right? Your phase error is constant from one cycle to the next cycle. So it's basically a DC phase error. That is, if I plot phase error versus time, right, this would simply be a constant. Or in other words, if you are working with Laplace, it means that you have to put s equal to 0. So the expression you will get is Vc under steady state would be equal to phase error into some factor. Right? Now you could have had other expressions, complicated expressions here, maybe 1 plus s into alpha by 1 plus s into beta. To get to the steady state average Vc versus phase error under steady state, you simply have to put all the s's to 0. Omega 0, that's all. Okay. Is that clear? Yeah. So now the plot, something is not clear? Okay. So now if I were to plot Vc versus phase error, you'll get a plot like this, alright, with the slope equal to ICP R by 2 pi. Now the next part of the question, prove or disprove. So the loop, the PLL ensures that the steady state phase error, yes.
And to do this calculation for some phi error greater than pi,
Phi error greater than pi and less than 2 pi. Okay, so we are dealing with the PFD. PFD responds only to the rising edges. So it will keep increasing.
So if phi error greater than pi, so the other positive will be hitting first, so down would be at pi error.
Phi error greater than pi would mean your ref is, if ref is like this, the other signal is right. So your up signal will go high here.
If you look at steady state.
Then the down signal will go high here. Then they'll come down. Right? Then the up will go high here, down will go high here, and then they will come down again. Right? This answers your question, right?
Yeah.
So the last part is you have to check whether the steady state phase error can be 0 for all values of omega out. What do you think? No? Everybody agrees? Okay. So a very quick way to see that is
It will start to like 1 omega out, 1 of the omega out. Because we control will be 0 and pi and 0.
So let me explain that. The omega out is given by the expression. This is equal to some free running frequency omega naught plus kVCO times the V control. So if I plot this with respect to Vc, for Vc equal to 0, this is at some omega naught, right? And after this, it's going to increase like this. Now, if the output omega out was equal to omega naught, that means your Vc value under steady state should be 0, right? Which means your phi error can be 0. Okay. Now let's say your omega out, because of how you have configured your M, right? Your omega out is expected to be much higher. Let's say it's somewhere here. It's some omega 1. So to sustain this, the VCO should get an input of some finite VC, let's say VC1. Now if VC1 has to be provided to the VCO, let's say this is VC1, that would mean that at the input of the PFD, you need to have some finite phase error. Is this okay? Yes. You can use final value theorem also. Right? So I'll come to that in a minute. Now, before we proceed, could you quickly comment on what this VC versus phi error plot will be for the loop filter that we have been currently using? So the loop filter in our PLL loop right now is some R1 and C1. Can you sketch what this VC versus phi error is for that case? What would be the expression for Vc of S? So there is some phi error into ICP by 2 pi 1 plus S R1 C1 divided by SC1. I mean, you can put, it's blowing up, right? So what it means is, for every value of a finite phase error, you can expect to see Vc going to infinity, right? Going to be very, very large. Or in other words, for phi error equal to 0, it's possible to get any value for Vc. Correct? Which is why when you use a loop filter like this in the PLL, right, you can have a 0 phase error at the input of the PFD. For a 0 phase error, you can have any value of frequency at the output. Yes.
If you're putting just a resistor,
yeah,
and you need an omega equal to omega 1,
right,
you will need a DC bias of VCO. Like you need a sustained voltage VC at the VCO to maintain that frequency.
okay.
But then here, if your phase error is 0, there won't be any current flowing through.
Correct. Same thing. The same thing that we discussed here. You are just approaching it from a different angle. Both of them are same. Is so much clear? Okay. So, can you quickly tell me what should be the type of the PLL be, right? Any comments on what type the PLL should be, such that you can have 0 phase error? So, what helped you here is a pole at 0, right? So the loop filter has to offer a pole at 0, right? Now in the PLL, you already have one pole here because of the KVCO. There is no two ways about it. If you have a VCO, you will have one pole at origin. On top of that, whatever is your loop filter should also offer one more pole, right? Therefore, you should have 2 poles at the origin. Right? So one pole at origin coming from here. If you want 0 phase error, the loop filter also should have a pole at origin. Right? Therefore, you should have at least 2 poles at origin to make sure that the phase error is 0. You have doubts? You didn't get it. Okay. So in this case, we said that it is possible to have a phase error of 0 and still have some finite value of Vc. That part is clear. That is possible because you have this 1 by S term. You have this S term in the denominator. In other words, this function has a pole at origin. Right? So now if your loop filter is offering you one pole at origin, it's possible to have a finite Vc even with 0 phase error. Okay? So the transfer function from here to Vc should offer you one pole at origin. Right? On top of this, the VCO already has another pole at the origin. Right? So you need the PLL to be at least type 2 to be able to ensure that you have a 0 phase error at the input for any frequency at the output. That is of course supported by the VCO. Is this okay?
Is there any reason why you need a phase error if you're only interested in the frequency of
So I'll come to that. So please remind me if I don't answer that by the end of this lecture.
Then phase error was 0.
Yeah.
You told that you were getting some frequency at
Correct. So which one in the initial case? Right. So in the initial case, your VC versus phase error was a curve like this, right? And so the when you're connecting R1C1. Okay, so even when the phase error is 0, right, for any value of Vc, you will have some omega out. The VCO expression is given by this. So whether Vc equal to 0 or some other finite value, it will follow this expression. So you will have some frequency. Right? So when Vc equal to 0, that frequency will be the free running frequency of the oscillator. If Vc is a different value, accordingly you will get a different frequency. Okay, so now let me quickly show you how you can also do this calculation using final value theorem. So your phi error of S is given by phi ref of S minus phi FB of S, the feedback signal, right? The phi feedback can be replaced as phi out of S divided by M. How can I write phi out of S in terms of phi ref of S? It is the closed loop transfer function from the input to the output, right? So that is given by M into L of S by 1 plus L of S, right? So you take phi ref of S outside. So you will have 1 minus L of S by 1 plus L of S, right? So this will simplify to be simply 1 by 1 plus L of S. Okay, so now if you have a phase step, so you have a phase step in ref, let's say your phi ref of t will simply take a unity phase step, u of t, right? Then what is phi ref of S? 1 by S, right? Now let's say you had a frequency step in ref. So then omega ref of t is u of t, right? What can I tell about phi ref of S? 1 by S square. Is that clear to everyone? So your phi ref of t is simply integration of omega ref of t dt. So this implies that phi ref of S will be 1 by S square. Okay. So now my phi error of S in the presence of a frequency step is simply 1 by S square into 1 by 1 plus L of S. Right? On top of this, you can apply the final value theorem. So that is phi error of t under steady state, basically limit t tending to infinity equal to, what is the theorem? Limit s tends to 0, s into whatever expression you have here. So you can solve this and see that only when you have a type 2 PLL, this will go to 0. Type 2 or a higher type. The question was for a frequency step, right? I asked you for all frequencies, whether you would be able to achieve 0 phase error irrespective of what the frequency is. So how you can think about that is, maybe it started out at omega naught initially and then it had a frequency step. So one way to model that question such that you can apply the final value theorem. Okay. Alright, so now we'll move on, come back to our type 2 second order PLL. So we have this is R1, C1, PCO divided by M, and this comes back as the feedback signal, right? So if you had only the capacitor, that is what you are thinking about, right? This system is not stable because you have one by S from here, another 1 by S coming out of this. You have 2 poles at the origin. This is unstable. The closed loop function will have 2 poles. Yeah, phase margin of 0. Yeah. So we wanted to compensate for this, and to do that we introduced a 0 here. So the small signal phase domain model of this is ICP by 2 pi. What is Z of S? 1 plus S R1 C1 by SC1 into KVCO by S and you have 1 by M here. This is okay? We calculated the closed loop transfer function from phi ref to phi out, and we also saw how to look at the 3 dB bandwidth of the same. So what was the expression? In terms of M and L of S? It's M into L of S by 1 plus L of S. So this was a low pass transfer function. Does it make sense intuitively? Why?
Equals to 0, the whole time goes to 0.
No, but looking at this loop, does it make sense?
Yeah, the same thing. Sorry. Last second.
So if your phi ref is varying very slowly, right? The changes in phi ref is very slow.
It comes to 0.
So all of these will give a very large gain, right? Therefore, the loop will try and make sure the error here is 0 or error there is very small, right? Which means whatever is the variation here, the same variation has to appear here. Only then it will get cancelled, right? Which means that same thing is appearing at the phi out. So for low frequencies, any change in phi ref will appear at phi out. For very high frequencies, this portion offers very small gain. Therefore, this node is not able to catch up with phi ref. Therefore, changes in phi ref is not appearing at the output. Okay. So now let's say I want to calculate what is the transfer function from the VCO phase noise to the output. Is that clear? Yeah. So what we are doing now is basically we are calculating all the signal transfer functions and the noise transfer functions. STF and NTF from different points. So let's say I am now interested in the transfer function phi out divided by phi n VCO, where I am modeling this phi n VCO as some noise that is added at the output of the VCO. This is some phase noise. Can you quickly tell me what the expression would be in terms of L of S and M?
1 upon 1 plus L.
This will be equal to 1 by 1 plus L of S. Right? For those of you for whom it is not clear, can you tell me what the transfer function of this portion alone will be in terms of L of S and M? M into L of S. Why? Because the loop has a transfer function L of S, right? But this is equal to whatever factor we want by M, right? So this factor will have a transfer function M times L of S. So now instead of adding phi n VCO here, I could add a modified version of that at the input, right? So I have to add phi n VCO divided by M times L of S. Right? The advantage of adding it at this point is this is same as adding the signal to the input. Right? There is no difference. So it's as if I have added the signal to this input, which means I can directly use the transfer function that we have already derived. Right? So I can simply write my phi out will be equal to the signal applied at the input, which is phi n VCO divided by M into L of S, into whatever is the transfer function from phi ref to phi out, right? And this transfer function is nothing but M into L of S divided by 1 plus L of S. And then you can cancel out these two and you will get the same result as well. Is this clear? So now if you are looking at the, let's say you are looking at the resistor noise, how would you model it? Where would you model it in the loop?
source.
Yeah, so it's a voltage source. So how should I model it here? We take a
Between the filter and the VCO.
between the filter and the VCO. What do I add? I add another source. Right? So I can add a source. Some Vn is getting added here. Why not before it?
Because that resistor and capacitance was there. Vn will come parallel to the resistor itself.
Vn comes series to the resistor.
You can add.
So now the thing is, there is some IC current flowing through this, right? That is going to develop some VC across it. So it's VC plus Vn is what is controlling the VCO.
So I can get Vn over here also, that doesn't matter, right? Vn won't change the.
So the quantity here is a current. In the model, the quantity here is a current, right? And the quantity here is a voltage. So if you are adding it here, you have to divide it by this transfer function so that you are looking at a current. That's all. You have a question? Right? So now if you have added it here, you simply have to divide it by this portion, right? And you can bring it to this end and then multiply with the closed loop transfer function to find out the transfer function from here to the output. Okay? So quickly tell me, what comments can you make about this transfer function? Is it high pass or low pass? So think about what L of S value is for small values of omega and for large values of omega. So for small values of, so I'm looking at the noise from the VCO to the output. For small values of omega, L of S is very, very large, right? Infinite when for DC, right? Which means the transfer function is going to be very, very small.
Is it a bandpass?
Why would it be a bandpass?
Is it high frequencies as well?
For very high frequencies, L of S goes to 0, right? And the pattern is L of S is increasing, right? It's not changing now. So you would expect to see a high pass transfer function for this, right? So let me bring an interesting point of discussion here. Now, the transfer function from reference to the output is low pass transfer function, right? The transfer function from the VCO noise to the output is a high pass transfer function. Okay. What sort of shape do you expect to see in the VCO noise? Let's say I'm sketching S phi n of VCO. What would be the shape be? VCO has phase noise. That phase noise has a PSD.
Yes.
We have seen VCOs before. What sort of PSD do you expect for the phase noise of the VCO?
It is one this and this, right?
Huh.
1 by f square, 1 by f
Yeah,
square.
so you would expect to see 1 by f cube corresponding to flicker noise at the input and 1 by f square corresponding to thermal noise. So around 0, you expect to see a profile like this. Right? Now, if I want to filter out the VCO noise, what comment can you make about the 3 dB bandwidth of this transfer function? Let's say there is some omega 3 dB.
Should be greater than that point.
Should it be large or small? That's all that I want to know.
Very large.
So if you want to filter out the VCO noise, then you want to push this as large as possible, right? That would mean maximum of these. So your transfer function will get superimposed like this, right? The more you are able to push it to the right, the more VCO noise you are able to filter out. Is this clear? Feel free to ask any questions if you have doubts. So in other words, the PLL is filtering out VCO noise within the bandwidth of the PLL. So the loop has a bandwidth, right? The loop bandwidth is roughly equal to the 3 dB bandwidth of all these transfer functions, right? So higher that value, more VCO noise is getting filtered out. Is that okay? Take a minute, feel free to discuss and then ask me questions. I can see some blank faces.
So this we are assuming that zeta is much greater than 1, so that we can assume that 3 dB and
That is 2 zeta omega n, but even if I don't assume that, right, if I increase the omega u of the loop bandwidth, all the 3 dB bandwidths will also increase. Just the trend, it will increase. It will be some factor of that, but everything is going to increase.
Omega 3 dB of both low-pass and high-pass can be same.
This will be roughly in the same ranges. For zeta much greater than 1, they are almost same. It will be 2 zeta omega n. But otherwise, they are very close to each other. So the critical part here is, if I increase this bandwidth is also going to increase, right? Yes, it should increase. Yeah. It's all part of the same loop. I'm simply changing where I'm giving the input from.
This changing
What do you think? Is it good?
it's giving more info. Kind of thing.
So if I assume that the reference is coming from a clean crystal oscillator, it will still have noise. That noise is typically white noise, but much lower, right? Now, it's not necessary that your reference will always come from a crystal oscillator. Sometimes you might give it from a controller where the reference itself will have a lot of phase noise. So now, if your reference is noisy, you should keep your bandwidth to be as small as possible, right? Now, once you do this, this bandwidth is also going to reduce, which means more and more of the VCO noise will now appear at the output. Okay, which means when you design your PLL, you have to burn extra power in the VCO and choose architectures that will inherently have lesser phase noise. Right? You cannot have a crappy VCO. Now, if you know that your reference is going to be very clean, right, then you can have a larger bandwidth in both the systems. Right? So more of the reference noise can come to the output, but reference is anyways clean, so it's okay. Right? And you have a very high bandwidth for the loop such that most of the VCO noise is getting filtered out. Is that clear? So in one of the previous classes, we talked about how for a standalone VCO, the jitter is unbounded, right? Because if you integrate under the curve, it can go to infinity. Now, because you are filtering it with a high pass transfer function, the phase noise appearing at the output will look something like this. Right? All these 1 by f cube regions can be filtered out by the attenuation offered by the high pass transfer function. The signal will appear as it is above the omega 3 dB, but by then the phase noise itself would have dropped considerably. So this is how you bring a bound to the VCO's phase noise. Is it okay? All right. So now we have seen two major transfer functions. One is from the reference to the input, then from phase noise to the output. I just mentioned how you can calculate the transfer function from the resistor noise to the output, right? I'll leave it up to you to figure out what sort of transfer function this is, whether it is high pass, low pass, band pass, or a notch transfer function. Similarly, you will also be able to calculate calculate the transfer function, let's say from charge pump noise. So you can add some charge pump noise in the form of a current here. You translate that to the input by dividing with this transfer function and calculate the total transfer function. Similarly, you can assume a divider noise and then calculate what that transfer function is going to look like. From different points in this loop, you can calculate the transfer functions. Okay. So then one more question to cover. So that is, earlier we said that if you have a type 2 PLL, in the absence of any non-idealities, you will have phase error equal to 0. Right? Now, in the presence of non-idealities, you know that static phase offset exists. Right? So you can have a finite phase error. Do you think this is a problem? So in most cases, we are interested in using the clock at the output, right? So if the clock is very ideal, I would simply see an impulse at omega out, right? But we now know that you can also expect a skirt around it, right? So for now, you can imagine that the skirt is still present, but I'll talk in terms of impulses, okay? Now let's say at every omega ref, if there is a phase error, in every period, some current is getting injected here, right? Which means in every period, there is some fluctuation in this VC node, right? And this fluctuation is happening at a frequency of omega ref, right? Now, depending on how this waveform is, it need not be sinusoidal, as you have seen from a DLL, right? Depending on how this waveform is, you will have higher order harmonics also. So you'll have omega ref, 2 omega ref, 3 omega ref, etc. Basically, you have n times omega ref. So the control node voltage going into the VCO has components at omega ref, right? Which means at the output, you will see that the components are going to appear at omega out plus or minus n times omega ref. So you can look at how the VCO was modeled, right? If you have, we have done this calculation once. So if you have a sinusoidal noise at some omega 1 at the input, that is at the VC node, at the output of the VCO, you will see components at omega out plus or minus omega 1. Right? We have done this once. Do you remember somewhere we calculated some deterministic jitter and all based on this? Right? So what you can expect to see is you'll have components around these points at a distance of omega ref, 2 omega ref, etc. Right? Now this is undesirable. What you wanted was a clean clock at omega out, but now instead you are also getting spurs at harmonics of omega ref, like modulated harmonics of omega ref, right? And this is called as, so what should we call these spurs as? Any suggestions? They are happening because of they are related to the reference frequency. They are happening because the loop is operating at the reference frequency. So we call them as reference spurs. Right? Now this is undesirable. If you were working with a wireline communication, they will come out as a deterministic jitter, right? Every certain periods, you will see a very deterministic shift in the edges.
One more doubt I had in this question. When it was only R, only R, it used to be V, it was V control average, right?
It was V control average, steady state value.
It was still, but that will, for some, more than most of the time, it will be 0 for.
So in taking the I flowing into the R, you have already taken the average of the I. That is why you have ICP by 2 pi.
No. C1 not there, only the question.
Yes. In the same question.
Because I out was, what was I out? It was just for the pi error into
Correct.
pi into.
So what is the average current coming out?
Something like that. ICP by
2 pi.
ICP 2 by 2 pi.
Yeah.
This will be the average current. But I am saying no. For the when the current was 0, not the average current. When the current was exactly 0, the whole period there will be
A period when the current is 0.
VC will be 0 for that time.
Correct.
Instantly it is 0.
Correct.
And omega in that VC going to directly fall to this. Then again it will go up. And again it will.
Right.
So the average frequency out will be up omega.
So if your output was a square wave shaped, right, and it is seeing the right frequency at the rising edges, so.
But at rising edge, it won't see the correct one, right?
So we can discuss this later, but what you will see is a distortion in the duty cycle. Duty cycle distortion will happen, yeah.
As the frequency, the average frequency or whole time period will be omega out, and the omega out.
Average frequency over the whole time period.
Will be the required one, not the. Here in this, even if I take one cycle itself, then I will get the frequency equal to omega out.
Correct.
What we require basically, the required frequency. When there, if you see, check the one of the instances, I don't think so it should be the same.
So can we discuss this after class? Right. So now I want to suppress these reference spurs as much as possible. Now the problem is happening because you have some ICP current, right? Some ICP current which is at omega ref flowing into the series combination of R1 and C1. Okay, so now I want to divert, if I could divert this current into an alternative path, right, I can suppress the fluctuations happening at this node. Is that okay? So any suggestions on how I can do this? But when I do this, I don't want to make a lot of changes in the loop also. Right? I could add a capacitor, right, to suppress it. So let's say I add another capacitor C2, right? So now what is this transfer function? So if I give a current at omega ref, so we are looking at the current component happening at omega ref, right? Then this will simplify to 1 plus j times omega ref into R1 C1 divided by j omega ref C1, right? Now this component is simply 1 by j omega ref into C2, right? All that I have to make sure that this magnitude is much larger than the second magnitude. Then most of that current will flow into C2 and you will be able to suppress the reference spur. Okay. But of course there is no free lunch. I have added an additional component into the loop, which means there will be changes in the loop dynamics, right? So let's quickly look at that.
We can add resistor to two cases.
So you are planning to add a resistor, right? Now if I add a resistor, you have some current flowing through this, right, causing a voltage drop across it. That voltage drop will happen whenever that ICP is flowing. It's not suppressing the voltage. Right? Now the other suggestion given is you can add an R and a C. Right? So now your VC voltage will be taken from here. Right? So this is another loop filter. So multiple loop filters are possible. You can have second order, third order, fourth order loop filters. Right? So all of these combinations are possible. So I'll just discuss one third order loop filter now. Right? So I'll just discuss this particular case because this architecture is quite popular, where you have a C2 connected here. Right? So can you quickly tell me the transfer function for Z of S? So 1 plus S R1 C1 by SC1 into 1 by SC2 divided by 1 plus S R1 C1 by SC1 plus 1 by SC2. So in the numerator you will have 1 plus S R1 C1. Denominator you will have SC2. So I'll take S outside. You will have C1 plus C2 plus S square R1 C1 C2. Right? So now I'll take the S outside in the denominator. So I'll take S outside and I'll also take C1 plus C2 outside. Then you will have 1 plus S into R1 C1 C2 by C1 plus C2. Okay? And this factor C1 C2 by C1 plus C2, I'll start calling this as some C equivalent. Okay? So quickly tell me, C equivalent, will it be greater than C1? It has to be lesser than both C1 and C2. This is a series combination of C1 and C2. So the C equivalent value cannot be larger than either of them. Okay, so now can you calculate, draw the small signal phase domain model with the new loop filter and calculate L of S. Just write the expression for L of S, then we'll see what approximation to make. So let's do this together. L of S will be equal to ICP by 2 pi. So we'll keep all the S terms towards the end. So there is KVCO. You'll have M from here into 1 plus S R1 C1 divided by S square into, I'll put the C1 plus C2 here, into 1 plus S into R1 into C equivalent. Okay. So tell me the 0 position. Minus 1 by R1 C1. What are the pole positions? So you have 2 poles at 0. And you have another pole at minus 1 by R1 into C equivalent. So far okay? Right? So what is the type of the PLL?
Type 2.
This is type 2 and order is 3. So this is a type 2 third order CPPL. Right? Let me also quickly plot the magnitude of L of j omega and the angle of L of j omega with respect to omega. Right? How do you think it will start? So this starts at minus 40 dB per decade.
Then go to minus 60. Okay, this will be small, this will be big. Then it will
So
be
do you
minus
think
20. Minus 20, you can go to minus 20.
So this pole is at a higher frequency than the 0, right? So you will first have the pole, you will first have the 0 and then you will have the next pole, right? So this is
assumption that it will come after the unity.
yes, I have made the assumption that it will come after the unity loop gain frequency, right? So this is your omega u and this is your omega p3, right? And how does the phase look like? Starts at minus 180.
Goes to 90 and then minus 90 and then comes back to minus.
Yes, it can get to minus 90 and then from somewhere here it will start to fall again and go back to minus 180. This is okay? So now your phase margin is basically this distance. If this is your minus 180 line, this is basically your phase margin. Okay, so now I have one last question on this, right? Let's say there is a phase margin constraint given to you and it turns out that you can meet the phase margin constraint whether you put your omega u somewhere here, right? So you can adjust the values of your gain, the positions of the poles and zeros such that you could have your omega u somewhere here or you could have your omega u somewhere here, right? Or the third option is you can still have your omega u in this region. So I'm giving you 3 options. If you had a choice, how would you design? Where would you put your omega u in this curve?
What time? Omega u.
You have to, let's say you have to decide where to place your omega u, right? By adjusting the gain, you will be able to shift the position of this curve and get an omega u. If you had a choice, where would you put your omega u? Why third? Somebody said third, no? Why third? So that you can get a larger bandwidth. So you are assuming third because this is if the VCO phase noise is a problem, right? But let's say you could have also pushed your omega P3 out, right? Such that the region still extends flat like that. So I want to know, given this phase graph, is there a reason why you would keep it here, here or here?
I think most probably.
2, any other answers? 1 or 3, anybody? So now all of you are very familiar with the issues with PVT, right? Let's say you chose to put your omega u in either 1 or 3. Now in the presence of PVT, you will have variations because of which your phase margin can degrade very rapidly because you are in a slope in this region, right? Therefore, you should try and put your omega u where the angle of L of j omega is maximally flat, right? So I'll leave this as a thought for you, right? What value you can solve and see what value you will get. So you basically have to take the derivative of angle of L of j omega, right, and equate it to 0. Okay? And what is the expression for angle of L of j omega? So that is 180. You have 2 poles at the origin, so this is minus 180 plus tan inverse of, because of the 0, you will have omega, so write it for omega by omega c minus tan inverse of omega by omega p.
From this, you will get omega u, right?
So because you are taking a derivative.
Putting constraint on the magnitude of the DC magnitude of the thing, right?
I've written an expression for angle of L of j omega. So you.
After derivation.
Yeah.
You will get omega u, right?
After derivation, you will get an omega where it is maximally flat. You make that your omega u.
Omega u, right? That is something. Now you fix the omega u. Now another thing constraint is my magnitude of at omega u should be 1.
Correct.
Then you are putting constraint that my DC magnitude of the DC amplitude should satisfy this condition, basically.
Yeah.
Then you are putting constraint on angle. Or maybe ICP or something.
Yeah, ICP, KVCO, you have a lot more parameters to play around. Right? M is usually determined by other system level constraints. Okay. So with this we come to the end of our course. So each of these topics, for example, if I were to take phase noise and jitter, there is a textbook written only about that. If you pick up oscillators, there are multiple textbooks written only on oscillators. Phase lock loop, again you will find multiple textbooks like this written only on these topics. So this course is meant to give you a flavor of all these topics and give you the basic theory such that now you are in a position to pick up any material and read through it and understand it, right? This is by no way a comprehensive class on all of these topics. One more question. When do you think the first PLL was designed? Give me a year, right, or a decade. 1990s, 1970s.
The PLL in the same manner or the way?
Just the idea of the PLL. So it need not be with respect to the transistors that we know, right?
It should be the way before the year statement.
Way before, so some decade if you can give me. During microprocessor expansion. But that is again after 1940s, right? We had the first IC in 1950 something.
Very bad, 19th century.
So the first reported work is from 1932, right? And this is much before even MOSFETs were used. Yeah. So the idea is that tomorrow nanowire transistors can come, very complicated transistors can come, but the basic concepts remain the same, right? You just have to figure out how to use that device as a switch and how to model it as a 2-port Y-parameter network with GM and GDS and other factors, and you will still be able to design PLLs using it. So a colleague of mine said a very bad joke that is so bad that it is good. So I'll leave you with that thought. Every day when you see your face on the mirror, please think of a face lock loop. Thank you.
Let's discuss it.